In section 8.1, we're looking at the law of sines, and we're going to use the law of sines to solve triangles. And we're also going to find the area of any triangle given the lengths of two sides and the included angle. Quick review here. Before, when we said solve the triangle, that meant finding the measures of all sides and all angles. So finding all side lengths and all angle measurements. It's still going to mean that same thing. We're going to look at an example from previous. This would have been in our chapter 6, and we're going to solve this triangle. So in this triangle here, it looks like for known measures, we know the length of this side down here as 6.3. And its name would be little z, since it's across from the angle big Z. So this is side little z, lowercase z. It looks like we also know the angle Q here as 37.1 degrees. And we know the angle capital W as the 90 degrees. So we need to know 3 pieces in order to solve any triangle, and I do know 3 pieces here, so I have enough information. Well, from here, since I know angle Q, and this is a 90-degree triangle, I'm going to be able to use some trig functions to find side little q and side little w. So with respect to angle Q, I know this is the adjacent side. So if I wanted to solve for side Q, I could use a tangent function to use the ratio opposite over adjacent. So we will start there. And we're going to say that the tangent of the angle 37.1 degrees is equal to the ratio of its side opposite, which is little q, over its side adjacent, which is 6.3. And then we would multiply both sides by the 6.3. And so 6.3 times tangent of 37.1 degrees would be equal to angle little q, multiplying by 6.3 on both sides, of course, is going to cancel the 6.3 on the right-hand side, giving us the q by itself. From there, we're going to grab a calculator, and we're going to need that calculator to be in degree measure. So let me get my calculator moved over to this screen here and shrink it up. The default's radians. I'm going to go ahead and switch this into degree measure because this angle was given in degrees here. So 6.3 times the tangent of the angle, 37.1 in degrees, gives us a value of 4.76 for Q. So I know my side length Q here is equal to 4.76 units, or I could round that to 4.8 units if I'm interested in keeping it at 1 decimal place. All right, so we know now side little q, and I can find the 2 missing things right now, which are angle Z and side W. I have choices on how to find each of these things. The simplest way to find angle Z is going to be through subtraction. Since there are 180 degrees in a triangle, I know 90 of them are already taken up with angle W. I can subtract 90 minus 37.1 to get angle Z. So let's go ahead and do that. I'm going to do this right over here. Angle Z is going to be equal to 90 minus 37.1 degrees. And so with that subtraction, 90 minus 37.1 gives us an angle measurement of 52.9 degrees. So Z measures at 52.9 degrees. And then the only thing that I have to find is little w. Again, I have two choices for how to do this. I can use a trig function, such as the cosine of angle Q or the sine of angle Z, or I can use the Pythagorean theorem, since I know the two opposite sides, the two non-hypotenuse sides of this triangle. Any of those are going to work just fine. I'm going to go ahead, though, and use the cosine of the angle Q, just because this side Q here has been rounded, so I'm going to have a more precise solution if I don't work from a rounded value. So let's go ahead and try this. Your choice, though. If you had done the Pythagorean theorem, that would have been absolutely fine. I'm just going to take a different path here. So I'm going to say that the cosine of 37.1 degrees would be equal to 6.3 over W. And if I do multiply by the denominator, I'm just going to put my W to the other side, and I'll need to divide off the cosine. So what if instead of the cosine, I had used its reciprocal function, which was the secant? So the secant of 37.1 degrees would be equal to W over 6.3. So I can need a new marker here. And now I could multiply the 6.3 over 6.3 times the secant of 37.1 degrees is equal to W. So I'm going to copy the top line here because it's already set up as 6.3 times the tan. I'm going to change that tangent function to the secant. So 6.3 times the secant of 37.1 degrees comes out at 7.899, which I have to round to two places as 7.90. So we'll round it that way. W is equal to 7.9. And now the triangle is solved. So we could list all of the sides. We can list Q as, let's go for one place on all of them, since even with two places I have just 90 there. So Q is about 4.8, W as about 7.9, Z as the given 6.3. So these are the three sides. And then our angles are 37.1 degrees, 90 degrees, and 52.9 degrees. Triangle is solved when you are able to know and list all three sides as well as all three angles. Okay. All right. The thing that made this triangle possible for us to solve was the fact that it is a right triangle. It has a 90-degree angle. In this next portion of the lesson, we're going to look at solving any triangle, including triangles that are not right triangles. So triangles that are not right triangles are commonly referred to as oblique triangles. And just like right triangles, we can solve any non-right or oblique triangle. We just need to make sure that we know at least one side and any other two measures are known. So we need to know at least one side and any other two measures. Given this, what are all of the possibilities for situations in which we can solve a triangle? We know that we need to have one side, and if we know another side and an angle, we're going to be able to solve the triangle. Given that we know one side, we also might know the angle that is between that angle and another side. So these are technically two different diagrams here. This would be two sides where the angle that is known is not between the two sides. This one is where it is in between the two sides. Let me draw a little diagram for this. In a situation where it is side-side angle, I would know, say, these two sides, and then the angle that I know would be one of the other two. It'd be like, say, this angle right here. Doesn't matter which of those two, but it's one of the angles that's not between the two sides. That's going to be different from a situation where I know two sides again. Doesn't matter which two sides, but in this case, I do know the angle that is between them. So side-side angle or side angle side are different distinct situations based on the location of that angle. It's also possible that I know all three sides and I don't know any of the angles. I can solve in this situation. I need to know at least one side. So the other possibility is that I know a side and two angles. And so in this situation, let's say I know this side and my possibilities for my angles. Let's see. In the side angle case, then I have two angles in a row and then the side. And then there's also the final case, which is where I know the two angles that are around a side. So this is going to be written as angle, side, angle. One side has to be known, like we saw before, but the diagram for this is going to be a little different because it does matter whether the angle you know is the angle across from the side or, you know, the two angles that are touching the side. So here I know one touching angle and one across. Here it's the two touching. So these are 5 distinct cases where the diagram is going to look differently. And the method used to solve these 5 possible situations may vary slightly from the other. Other possibilities that are not in this list right here, so cannot solve, just to make a note, we cannot solve a triangle where only angles are known because you have to know at least one side. The reason for that is if you only know angles on a triangle, that triangle could have those exact same angles but be of a different size. And therefore, it's not possible to find the sides, right? Because similar triangles can have different side lengths. So that's why it's not possible to solve if I only know the angles, because they can have different side lengths. But as long as I know at least one of the sides, I can know 2 sides and an angle in 2 different ways. I can know all 3 sides, or I can know one side and then 2 angles, and again, 2 different ways. Okay? So we'll be able to solve any of those situations. But I am going to need to use the law of sines in order to solve these. So let's talk about that law of sines. Now that we know that we can solve oblique triangles, we need to develop a way to do so. So we're going to start with this generic oblique triangle, triangle ABC, and you can see that we have A, B, C, forming this triangle here. So it's definitely an oblique triangle. It need not be an acute triangle. So this particular oblique triangle is acute because each of these angles is below 90 degrees. It does not have to be. So it just happens to be the way this one was drawn. You also could draw an obtuse angle and make your triangle that way. No big deal. We're going to be able to solve an obtuse triangle the same exact way. So we're just going to begin with this diagram. Now, one of the ways to figure out the law of sines and to think about it is to imagine a straight line dropping down from one of the angles. It doesn't have to be this angle. You can, let's see, this one was by flattening this side to the horizontal. So you can flatten any of these to the horizontal and imagine that if this is flat on the horizontal, you could drop a straight line from A down to be perpendicular to it here. Okay, so this can be done for any of the sides. We're going to start with it's dropped such that it's perpendicular and therefore forms that 90 degree at this other point right here. All right. Now how this is going to work is we're going to think about angle A in terms of its sine. So the sine of angle A here would be the opposite. The original definition of sine was for right triangles only. So we're going to do its opposite as the side H over its hypotenuse. We're looking at this triangle here, which is B. Now, H is not inside this triangle, so we're going to need to solve for H or get rid of it. So I'm going to actually multiply that B over and say that H is equal to B times the sine of A. Okay. Now, if I look at angle B and I consider its sine, opposite over hypotenuse, it's going to be H over A. And so if I multiply by A, H would be equal to A times sine of B. Now, we're going to say we know that H is equal in these two statements. So therefore, if H is equal to H, it must be true that B sine A is equal to A sine B. These two lines must be equal. Rewritten, we can divide the B over to this side and the A over to this side. So rewritten, that's going to look like sine of A over side A, dividing both sides by A and dividing both sides by B, sine B over side B. Okay. The reason for that rewrite is it makes a ratio of the sine of an angle to its opposite side. So we can drop altitudes, aka perpendicular lines, down from other sides. Like this looks like approximately 90 degrees. I'd need to measure it. But I could drop this hypotenuse, give it a name H, and I could do similar lines for the other vertices. And then I would be able to do one about side C, and I can get the relationship similarly that sine of A over little a equals sine of C over little c. Or I could drop a perpendicular line here. See, if I wanted 90 degrees, it's probably going to be right here for this particular triangle, and do the same kind of setup. Based on the same exact argument we did on this first one, we'll be able to come up with sine of B over little b equals sine of large C over little c. Okay, so we can get all of these ratios, and that's going to pair up any possible side and angle combinations. A and B, A and C, or B and C. The result holds true regardless of what kind of triangle we have. So we can do this for any oblique triangle. So we've made this mathematical law for any triangle. It's called the law of sines. Sines because it's the sine function that's used here in any triangle ABC. Now, I did write mine with the sine function on top. They've written theirs with the sine function on bottom. And I want to ask if that matters. And you should recognize that it doesn't matter because these are reciprocals of each other. So if you say, for example, 2 equals 2, then the reciprocal 1/2 equals 1/2 is still true. So I'm going to write in my version here as well. It's something that we're going to want to be able to use interchangeably. So either side A over sine A equals side B over sine B equals side C over sine C, or sine A over side A equals sine B over side B equals sine C over side C. In these cases, again, angles are all using capital letters. Side lengths are all using lowercase letters. Pay most attention to C because it can look very similar in shape. Little c is the side length. Capital C is the angle length or the angle measure. Okay. All right. So we've got ourselves that law of sines, and it can look like either the ratio pairings that have the side on top or the sine on top, just a reciprocal relationship. Let's go ahead and use this now. Now that we have that general purpose law that works for any triangle, we can do some deductive reasoning and apply it to solving triangles where we know at least 3 pieces of information. We're going to start here with looking at situations where we know 2 angles and a side. So we had 2 types of those. We had our SSA and our SAS type triangles. 2 angles and 1 side. So either SSA or SAS. Okay. So in our first example here, we are given angle B, angle C, and side B. So let's make a quick drawing. Doesn't matter what your triangle looks like, just draw a triangle. And then we're going to assign A, B, and C to this triangle. Doesn't, again, matter very much where those are. You can look at the measurements and try to eyeball which side is which. And it looks like I've done an okay job. So if this right here is 38 degrees as the measurement for angle B, this one's a little tighter, so 21 degrees is the measurement for angle C. Now, I don't know how big angle A is yet, but I do know that side B, which has to be across from angle B, must be here. And that has a measure of 24. So those are the things that I was given that I know for this one. I know that pairing of angle B and side B, and I know the measure of angle C. I need to find the rest. I need to find the pairing side little c. I don't know that one. And I need both parts of A. I need to find angle A, and I also need to find side little a. So the things I need to know, there's 3 things I know, and therefore there are 3 things I need to know as well. I need to know little c, capital A, and little a. The angle is going to be the easiest thing to find because I know for angle A, there are 180 degrees in a full triangle, and I've already used up 38 and 21 degrees. So if I subtract those off, I'm going to get angle A. So we can use just subtraction to find that missing angle. So angle A has to have a measure of 121 degrees. So it looks like when I sketched my triangle, I did not represent that wide enough to demonstrate that it's 121 degrees. But the triangle is really just so I can see the relationship between the positioning on the values that I need. Okay, so I'm going to write down all my angles. I don't know why I did 8 degrees. It's angle A. Angle A is a measurement of 121 degrees. Angle B has a measurement already given to us, as 31 degrees, and angle C has a measurement of 21 degrees. It's not strictly necessary to write the angle symbol in front of each of these. Just writing ABC is absolutely fine, and we know that they're angles because they're capital letters and because we've given answers in degrees. Okay, continuing, I need to find little a and little b, or little c, sorry, little a and little c. I know little b. This is where law of sines is going to come in. I'm looking for a side length, so I'm actually going to use this version since the unknown is going to be on the top. Later on, we will use this version when the unknown is an angle. That's not the case in this particular instance of it. So let's go ahead and find, let's talk about which ones we can find. So I have to use the BB pairing since there is one that I know both parts of. I know little b and sine b. So I'm going to have to use little b and sine b as one of my fractions. Then I can use either angle C to find the missing side C or angle A to find the missing side A. We're going to need to end up using both of those, but I'm going to start with this version right here because the initial information I was given was angle C. So let's just go ahead and find little c first. So we're going to use the fact that B, little b, is a measure of 24 in length over sine of B, which is 38 degrees. That's going to equal little c over the sine of C, which is 21 degrees. Okay. Now, to solve for C, I'm going to multiply that sine of 21 to both sides. And that's going to get us that C by itself. So 24 sine of 21 over sine of 38 is equal to little c. Okay, make sure my calculator is still in degrees. I believe that it is. Just wanted to double check. And let's enter this whole fraction here. We need 24 times the sine of 21 degrees over the sine of 38 degrees. And that gives us a value of about 13.97 for side C. So side C is about 13.97. We found that measure now. And I need to find A, little a. Previously, when we solved triangles, we could use a lot of different techniques. Once you know two sides, you could use Pythagorean theorem to find the third. That is not going to work here because this is not a right triangle. You do not have two perpendicular sides and one hypotenuse. So the only way to find side A is going to be using another one of my law of sines ratios. Now that I am looking for side little a, I have to use the first fraction, but I do know both side B and angle B, and now I know both side C and angle C, so I can use either one of those along with it. I'm going to stick with B because that's the one that was given, so it doesn't have a rounded value like my little c does, but you can use either one. Let me go ahead and use these. So I'm looking for little a over the sine of angle A. Remember that we figured that out already as 121 degrees. It's going to equal the measure of little b, which is 24, over the sine of B, which is 38 degrees. Once again, we're going to multiply our denominator over. This denominator over, because this is the side I need to find. So I'm going to multiply the sine of 121 over. So A is going to equal 24 times the sine of 121 degrees over the sine of 38 degrees. That's the one I'm trying to multiply over. on both sides, sine of 121 degrees, so that we're able to get side A by itself. With our calculator, we need to multiply 24 times the sine of 121 divided by the sine of 38, and we get a measure of 33.41 units for side little a. All right, we know everything, so our triangle is solved. We've written down our 3 angles over here. I don't have space to write underneath, so I'm going to write over here for my 3 sides. A is 33.41, B was already known at 24, and C is 13.97. It's nice to restate the angles and the sides because when you're doing work like this, the answers could be just in a bunch of different places. Organizing and putting all the angles together and all the sides together is just a handy way to make sure that you have all of your answers and that your teacher can find all of your answers as well. All right, that triangle was solved. We did have to use the law of sines twice on it because it was not a right triangle. And we were able to find this missing angle with subtraction. Let's take a look at the next one. Okay, example 2. Apollo astronauts used trigonometry to determine the width of craters. They marked 2 points A and B on opposite sides of a crater, and then they located a third point C, a known distance away from point A. By measuring the angles BAC and ACB, they're able to use the law of sines to determine the width of a crater. Draw a diagram that shows how this might look on a map. So I'm going to imagine what a crater looks like. And we are attempting to determine the width of the crater. And so we're going to mark 2 points, A and B, on opposite sides of the crater. So I'm going to mark point A here. And we're attempting to determine the width of the crater. So I'm going to mark point B here. Then we're going to locate a third point C, a known distance away from point A. So let's just say here, where I'm able to measure that distance. Now that distance is not likely a right angle, so we make it look like a little more like it's not straight up, just from the way I drew this picture. Could be obtuse, it could be acute, I don't know yet. We're going to find out some more. Okay, and then I can imagine this triangle here being formed. Does not need to be a right triangle, but I'm going to be able to measure the angle BAC. So BAC, that's this angle. So I'm going to be able to measure, let me color code these. The angle BAC is this angle. It's also what I might call the angle A. And I'm going to be able to measure the angle ACB. That's what I might call the angle C. If I go from A to C to B. So angle C. So I'm able to get on this side of the crater and then use some sort of measuring device to measure the angle from angle A. I can move to C, measure the angle from angle C. I can't get across the crater because it could be miles wide. I'm not sure how wide it is. Okay, but I can make this diagram, and I know angle A, angle C, and the other thing that I do know is that distance between angles A and C. So I'm going to know this distance here as well. All right. Now we'll put some values on this diagram. So let me re-sketch this diagram just a little bigger so I have room to fit values on it. So this is where A, C, and B are. And I know that C is 50 meters from A. So this distance now is going to be 50. That's the distance along that portion. And I know that angle BAC, that's the one also referred to as angle A, is a measurement of 112 degrees. Okay. And then I know that angle ACB, that's also known here as angle C, is 42 degrees. And my goal is, what is the width of the crater? If this is angle A, that would be side little a. If this is angle B, the side I know is side little b. And if this is angle C, this is the side we're going to call little c. What I'm being asked for is the width of the crater. Remember, the width of the crater was this value across to the bottom. That's going to be our side C. So I'm not being asked in this situation to solve for all of the values, but I'm being asked to solve for specifically little c, which was representing the width of the crater in our original diagram here. All right, in order to do this, I do need a pairing of a side and an angle. So I know the angle A, but I don't know side A, so no pairing. I know side B, but I don't know angle B, so I don't have a complete pairing. And I know angle C, but I don't know side C, so again, no complete pairing. So it looks like the law of sines is not the first thing that I can do since I have no pairings. What I'll need to do first then is actually find angle B. That's the only thing I'm able to find initially. Since I know two of the angular measures, I can find angle B with subtraction. So angle B is going to be from 180 degrees minus the 112 degrees minus the 42 degrees. So 180 minus 121 minus 42. B measures at 17 degrees. Now I've got a pairing of a side and an angle, and I need side C. So I'm going to pair up the unknown side C with this angle. So we're going to be using side C over the sine of angle C, which is 42 degrees. That's going to be equal to side B, which is 50, over the sine of angle B, which we now know is 17 degrees. We're going to multiply the sine of 42 to both sides. That's going to allow us to get side C by itself. Side C is going to equal 50 times the sine of 42 degrees over the sine of 17 degrees. My calculator should still be in degrees. So we'll take 50 sine of 42 over sine of, so it's supposed to be in the denominator, over, there we go, the sine of 17 gives us a C value of 114.43. It's likely that only one decimal place is needed here in terms of accuracy from the angle measurement. And then we'll just put some units on here. That side is approximately 114.4 meters. So that's the approximate width of the crater. All right, so just a quick recap of these last two examples. In the first example here, the triangle that I was given initially did give me two angles on one side. I apparently need to be able to read better. two angles and one side. So I listed the types for two side and an angle. What we have is two angles and a side. So that was angle, angle, side, or angle, side, angle. Those are the types I was given. You guys probably already noticed that I was being silly on that. This one that I was given was the angle, angle, side case, where the two angles were next to each other and the side followed it. This type over here was the angle, side, angle case. So we did see one example of each of those cases where two angles and one side was known. Now we are going to look at the side, side, angle case, or the side, angle, side case, where we know two sides and one of the angles. One of the things to keep in mind in this situation, unlike the previous where I know two angles and one side, if I already know two angles, there's only one possible answer for the missing angle. We use subtraction, we get our missing angle. If we know a side, consider solving triangles for which a side and an angle are known, in addition to the one side requirement. So that means that there are two sides because you have to know one side. So this is phrased a little strangely. A side and angle in addition to the one side length requirement. So it really means that there are two sides and an angle all together. Okay. In this case, it is possible to have situations where there are no solutions, one solution or two possible solutions. So we're going to have to proceed with caution when solving this kind of triangle. All right, so in this first one, I know angle C. I do not know angle B or angle A, but I know side little b, and this must be side little c. I do not know anything about A, angle A, or side A. So I am going to have to begin working with a pairing that's going to use angle C and side C, since that's the one complete pairing that I know. And there's actually only one thing that I could possibly find first here. Because I know because I know side B, I'm gonna have to find angle B first. I can't find anything about A since I know neither part of its pairing. All right. So for this ratio, I'm going to write down the general formula. We know we can do C over sine C equals B over sine B, or we could have had that flipped as sine C over C equals sine B over B. So just running down my formulas I'm going to work with here and then selecting and thinking about the reason for my selection. What I'm looking for is going to be angle B. I don't want the thing that I'm looking for to be in the denominator. I want the thing that I'm looking for to be in the numerator so I can multiply the number in the denominator over and get this by itself without having to do an extra division. So that's going to tell us that we're going to work with this version of the law of sines that has the sines on the top since it is an angle that I'm looking for. Okay. So let's get that started. We have sine of angle C, which is about 45.6 degrees, over side C, which is 34.2. And this is going to equal angle B, and I don't know the sine of angle B. over side B, which is 42.1. As we mentioned, we're going to be able to multiply that 42.1 over to both sides. And that'll give us 42.1 times the sine of 45.6 degrees over 34.2 equals the sine of B. Okay. Now I can get the decimal for this, and I will. Let's go ahead and do that. 42.1 times the sine of 45.6 divided by 34.2 comes out as approximately 0.8795, and that's equal to the sine of B. From there, since I need to solve for B, we're going to need to do the inverse function. That's going to be the arc sine of both sides. So we'll have the arc sine of 0.8795 equals the angle B, right? Imagine doing arc sine of both sides. And then arc sine and sine being inverses, so they're going to return the angle B. All right, so arc sine, and I'm going to copy this whole number, or actually, if I was planning ahead, I could have typed that entire fraction right inside the arc sine function. Keep in mind that my calculator is still in degrees. I need it to be in degrees, so I'm going to give an answer that is in degree measure, so it is still in degrees. And I've got myself an angle of 61.58 or 61.6 degrees. And I'm going to round that to one place. I'm going to keep the 5/8 right now. Degrees for angle B. I also need to keep in mind that when I solve an arc sine function, I remember that the range, the outputs of the arc sine function are going to be strictly in quadrants 1 and 4. So the angle that I got right here has a matching answer over here in quadrant 2. So I also need to go ahead and find that angle. So this right here is the angle about 61.6 degrees. That is the same reference angle that I'm going to have in quadrant 2. So in quadrant 2, this is where 180 degrees is. This matching angle is going to be shy of 180 by 61.6 degrees. So if I take 180 minus that 61.6 degrees, it gives me another possible solution. 180 minus 61.6 gives me a possible solution of 118.4 degrees. So right now, for angle B, we have two possibilities. We have maybe B is 61.6 degrees, or maybe angle B is 118.4 degrees. Okay, now, it's possible that we're going to have 0, 1, or 2 possible solutions. It looks right now like I have 2 possible solutions, but I'm not going to know for sure if both solutions are viable until I try solving the rest of the triangle using both of them. Sometimes I'll find that the 118.4 degrees, for example, is just too big for this triangle to work out, or vice versa. Maybe the 61.1 is too small for this triangle to work out. So we need to solve the rest of this triangle twice. Okay. I can tell I'm going to need a bit of extra paper, so I'm grabbing an extra sheet here. And let's look at the case if B is equal to 61.6 degrees. And let's work through that case here. So this is going to be solving this situation. I'm probably going to use more than this space, but I'm going to try to begin there. What if B is 61.6 degrees? Then I know two angles, since C for sure is 45.6. So I'm going to find angle A. And angle A would be 180 degrees minus the 45.6 degrees minus the 61.6 degrees. So 180 minus 61.6, I guess I'm subtracting the other order, that's fine, minus the 45.6. That would give angle A a measure of 72.8 degrees. Let's think what we know. So now I know angles A, B, and C. I already knew side B and C, so I just need to find side A. I had to wait to find side A until I knew angle A, and I'm looking for a side, so I'm going to set the ratio up when it has the sides in the top. So A over sine of 72.8 degrees is equal to, I can use either the B or C ratios, doesn't matter. Let's set this up with the C ratios, since those are the two that were known. So the C ratio, that's going to be 34.2 over the sine of 45.6 degrees. We know that in order to solve this, we're going to multiply the sine of the 72.8 over to the other side. I'm going to go ahead and start writing on my extra paper here. So A is going to be equal to the 34.2 times the sine of 72.8 degrees over the sine of 45.6 degrees. Just multiplying this guy over to the other side there. And let's evaluate to find side little a. 34.2 times the sine of that 72.8 degrees divided by the sine of our 45.6 degrees. This gives us a measure for side little a of 45.7. So in this version of solving, we have the potential solution where angle A is 72.8 degrees. Angle B was 61.6 degrees. Angle C, that was known to us as 45.6 degrees. And then side little a is 45.7. Side little b was 42.1. And side little c is 34.2. Okay, so we've got ourselves a solution. We're going to briefly check this solution for any obvious errors. Obvious errors would include having the largest angle not have the largest side. So we know that the largest angle must have the largest side, and conversely, the smallest angle must have the smallest side. That does seem to be true. So there's nothing obviously incorrect about the solution, in which case I would throw it out. So we have ourselves one possible solution. We're going to see if there's a second one. Now we are going to look at solving this in the case where B instead is the 118.4 degrees. So we're going to solve this case. What if instead B was 118.4 degrees. Well, in this case, I can find that angle A would have had to be 180 degrees minus the 45.6 from angle C minus the 118.4 degrees from angle A. So angle A is 180 minus 45.6 minus 118.4. So in this case, angle A would have been equal to about 15 degrees. Oh, I'm sorry, I mistyped 45. 16 degrees. Angle A would have been about 16 degrees. If that had come out negative, we would have immediately learned that this angle was not viable, but it did not. So this angle is still a viable solution. Let's continue to look at it. And we're going to find the length of side A. So in this case, A over the sine of 16 degrees would be equal to, we can do the ratio of either C over angle C or B over sine angle B. Doesn't matter. I'm going to actually stick with C since those are the pair I was given. So the 34.2 for side C over the sine of the 45.6 for angle C. And we're going to multiply the sine of 16 over. So 34.2 times the sine of 16 degrees over the sine of the 45.6 degrees. 34.2 sine of 16 over sine of 45.6 degrees gives us a measure for angle A of about 13.2. So in this version of the solution, we have angle A being 16 degrees, angle B being 118.4 degrees, angle C being the 45.6 degrees we were given. Little a comes out with a length of 13.2 degrees. Little b comes out with, that one was given to us, 42.1. And little c was given to us as the 34.2. Let's check this for any obvious flaws. The largest side should correspond with the largest angle. Yeah. Smallest corresponds with smallest, so that also checks out. So there are two completely valid solutions to this triangle. I'm going to make myself a note about this. Both solutions work. So there are two possible solutions. And there's really not a good way of knowing which one is correct. Now, if I do look back at the initial diagram for this one, that angle A is really small. So it's very unlikely that angle A was supposed to be 72 degrees. It's very likely that from this diagram, if this diagram was drawn to scale, the second solution that had the B that we had to work for, that it wasn't the one the arcsine gave us, it was the 118, is actually the one that matches this diagram. But if I had to draw the diagram myself, like I do in the case of this one here, there's going to be no way for me to know how to draw initially. So there's going to be no way for me to know which solution is correct. If this has been drawn to scale, then this one would be the correct solution. I don't know for sure that this is a to scale drawing or just a regular old triangle drawn with markings A, B, and C on it. So I, in that case, know that there are two ways that this triangle could have been solved. Okay. All right, so I'm going to continue on to the next problem. In the new course pack version, this will be on the next page because this problem just takes a lot of space. But for right now, it's on this page, on my page. So I'm going to come back here to example 4, where I need to solve the triangle ABC given side B, side C, and angle C. I'm going to draw myself a triangle. I don't know where A, B, and C are supposed to be, so I'm just going to draw any old triangle so I can label things on it. Here I know that side B, which is across from angle B, has a measure of 4.157 kilometers. Side C, across from angle C, this capital C here is kind of small. I'm going to try to make it a little bigger, has a side length of 3.446 kilometers. And angle C in here has a measure of 51 degrees, 48 minutes. So I've got myself a pairing of side C and angle C. So we get to work with those C's again. And the first thing I'm going to have to find is going to be angle B again, since I happen to know side B. I can't do anything with A because I don't know either the angle nor the side. Okay, let's work on finding that angle B. Since we're finding an angle, we're going to start with the signs on top. So let's start with sine of B over side B, which is 4.157, equals the sine of angle C, which is 51 degrees, 48 minutes. And side C, which is 3.446, and we'll multiply our denominator over. So sine of B equals 4.157 times the sine of 51 degrees, 48 minutes over 3.446. So 4.157 times the sine of, we know we can enter 51 degrees, 48 minutes as 51 plus 48 60ths, since there are 60 degrees in a minute. And we'll divide this by that 3.446. So sine of B is about 0.948. I'm going to have to round to 8 instead of keeping that as 7,999. 7. And then I can use the arc sine as the inverse of the sine function. So B is going to equal the inverse sine or arc sine of that 0.948. I'm going to do B equals in a minute because I'm going to need to do my picture here and figure out both possibilities for angle B. Okay, so let's get that arc sine going. Arc sine of, I'm actually going to just copy that whole statement, paste it in, so I have the exact value here. So one possibility for B is that it is 71.4 degrees. That would be in quadrant 1. So the other possibility is that if the sine value is positive, it's going to have to be in quadrant 2. That's why I know it's in quadrant 2, because the sine value is a positive 0.9. That's going to happen up here in one of these two angles. So the other one is going to be 71.4 degrees shy of 180. So the other possibility would be 180 minus 71.4. So that's 108.6 degrees. So we've got two initial possibilities here for two initial possibilities here for angle B. Let's see if we can find the angle A's that would match up with these. Okay, so in this first case, angle A, we're going to take the 180 minus the 51 degrees, 48 minutes. I have to convert that back to minutes here in a second. minus the 71.4 degrees. Let's see if we can get a measure for angle A. So 180 degrees minus 51, let me put parentheses here, minus 51 degrees, 48 minutes, and then minus that 71.4 degrees. In this case, the decimal version of the angle would be 56.8 degrees. In the other version, I would take 180 degrees minus the 51 degrees, 48 minutes, minus 108.6 degrees. Just going to copy this and change the angle that I subtract to 108.6 degrees. And this version of angle A would be 19.6 degrees. Okay. Both of these came out as positive, so I have no obvious issue with the size of angle A. So we're working with, again, those two possibilities for solutions. And in order to find out if they're both still valid, we're going to have to solve for side little a. I'm going to grab another sheet of paper here, and we'll go in the case of if B is the 71.4 degrees. Let's go ahead and now write that in DMS notation. So that angle was right here. So copy, paste, and we know that's 71 degrees. And then we want to figure out how many minutes. So I'm going to take off the 71 degrees, and we're going to multiply by 60. So that's 71 whole degrees, and then it's about 26.5 minutes. And our original angle was just down to the minute, not down to the minutes and seconds. So I could probably round this to 71 degrees and 27 minutes. Or I could take off the 26 and then convert my minutes into seconds. Let's just go ahead and say we want this rounded to the nearest whole minute. So we're going to say this is approximately 71 degrees and 27 minutes. So our corresponding angle A, let me put the exact value here as well. Our corresponding value for angle A came out as 56.8 degrees, which is 56 degrees, subtract off the 56, and multiply by 60, and that's about 46 minutes. Okay. We're looking for now side little a. So side little a will be over the sine of 56 degrees, 46 minutes. And since I knew the full C pairing, let's go for side C of 3.446 over the sine of C, which is 51 degrees, 48 minutes. We're going to multiply the sine over, so little a will be equal to 3.446 times the sine, we're multiplying the sine of 56 degrees, 46 minutes over over that sine of 51 degrees, 48 minutes. So our sine of 56 degrees, 46 minutes, divided by the sine of 51 degrees, 48 out of 60 for, oops, I was supposed to have a plus, 51 degrees and 48 out of 60 for 48 minutes. Little a comes out as about 3.67. So in summary, for this option, A is 56 degrees, 46 minutes. B is 71 degrees, 27 minutes. C is 51 degrees, 48 minutes. Side A is 3.67 units. Side B was given, I guess I should have kept 3 places. I just saw that B here was in 3 places, 4.157. And side C is 3.446. So if it's not too late, we can see that this would have been 668. So 668 if we want 3 places because we had 3 places on the other sides. Okay, we have one possible solution. Let's check it out. Biggest angle, biggest side, smallest angle, smallest side. That sounds good so far. See what we find for the other option. What if instead of B being 71.4, B was equal to that 108.6? That 108.6, let's try to get that into DMS. So that 108.6 was really this number. And I know that that is 108 degrees. So let's subtract off that 108 and multiply by 60. So about 34 minutes. This would make A so we did this here, so let's copy that again. And instead of 0.6, let's subtract off the full set of decimal places here. So our A, we said it was 19.6, and that 19.6 degrees is 19 degrees with approximately 38, so 38 minutes. Need to find our last little piece here, the missing side length for little a. Little a over the sine of that 19 degrees, 38 minutes. We're going to keep the C pairing just because we had that information already. There's no chance that we are the ones introducing rounding error. 51 degrees, 48 minutes. And we're going to multiply our sine over again. So A is equal to 3.446 times the sine of 19 degrees, 38 minutes, over the sine of 51 degrees, 48 minutes. Okay, we have something like that typed here. So let me copy that just to save us some time. Sine of, let's change this here on the top to be 19 degrees 38 minutes. The rest of it is still good because those came from C, which we're using again. So this will give us a little a measure of 1.473. So A here is 19 degrees, 38 minutes. Side A is 1.473. B here is 108 degrees, 34 minutes, with a side length of 4.157. And C was 51 degrees, 48 minutes, with 3.446 for its side length. Smallest, biggest. So we have everything looking okay in this alternate possible solution. So we've got ourselves two possible solutions again. This one, I have no indication of which one might be correct. If just one is, they are both correct. So once again, we have two possible solutions. It, of course, takes twice as much time to solve any equation that has two possible solutions than it does if there's only one possible solution. So these can get understandably a bit long. We're going to keep in mind that it's possible that you have two solutions anytime you know two of the sides and just one of the angles. And it's because when we do the arcsine, multiple angles may present as possibilities for an angle. Okay. We've got another example on the next page. In this triangle, we are given it's called SFT, and we are given that side F is 56.78 in meters. Again, arbitrary positioning of those. What matters is that I position the angle across from the side of the same name. So side T must be across from angle T, and it has a measure of 56.78. And the angle that we're given here, angle T, is 83.78 degrees. Okay, let's solve this one. Due to the fact that we have information about both side T and angle T, we're going to have to use that information. And the very first thing that we're going to need to find is going to be this angle F, since the only other piece of information we know is about side F. So let's start off with our sine of angle F divided by the side length of F, 56.78, and that's going to be equal to the sine of angle T, 83.78 degrees, over side length T, 56.78. Sine of F, if I multiply the 56.78 to the other side, times the sine of 83.78 degrees over the side 56.78. It's going to get me sine of F. And I'm just going to go ahead right now and do the arc sine of both sides, getting me angle F. So angle F is going to be equal to the arc sine of 56.78 times the sine of 83.78 degrees over 56.78. I guess I didn't need that parenthesis there. All right. So arc sine of 56.78 56.78 times the sine of 83.78 over 56.78. I was just double checking. I was saying that these looked like the same. I just wanted to make sure they were the same here. 56.78, 56.78. Just wanted to make sure I hadn't messed up my values. I noticed that they were the same at this point. I wanted to double check. That's what I was doing. So it looks good. And we come up with an F value of 83.78. However, there is the possibility that we have the partner in the other quadrant. So the partner in the other quadrant would have the same reference angle and therefore be shy of 180 degrees by that same amount. So 180 minus the 83.78. So the other possibility for F is going to be 96.22 degrees. So far, we have two possibilities for angle F. We're missing angle S according to our diagram here. So now that we know angle T and angle F, it's not a big surprise to me after observing that these have the same measure, that these angles have the same measure as well. If I have two side lengths that are the same length, I should get two angles that are the same length, although it could have been the other angle that was the same length. We'll see if that's going to work out. So we're going to find the corresponding possible angles for angle S here. Angle S, let's see, 180 minus 83.78 for angle T minus 83.78 for angle S. F would give me a measure for angle S of 12.44 degrees. With the other option, 180 minus 83.78 for angle T minus 96.22 for angle F would give me 0 for angle S. So in this case, we are not going to have a completed triangle. It would collapse into a line. So this is going to be not possible in terms of a triangle. So we know that this set of answers isn't going to work. This is going to lead us to one solution here, and we need to find that missing side, side S. So side S over the sine of angle S, the 12.44 degrees. Get rid of decimals here for a second. Equals, I'm going to use the TT pairing here. Side T, 56.78 over sine 83.78 in degrees. Angle S, or side S, this is a little s, small s is going to equal 56.78 times the sine of 12.44 degrees divided by the sine of 83.78 degrees. Let's evaluate this and find ourselves side length little s. 56.78 times the sine of 12.44. If I take off the implicit multiplication sign, my fraction is going to look like I was hoping it would. So sine of 83.78. Again, you can put parentheses around these. It's not absolutely necessary, so I've not been writing them in. And this gives me a side length of 12.3. I'm going to write down the 0 since the others were in 2 places. And units as well. This is in meters. Okay. All right. For a conclusion, I'm going to go up top here. We had angle S equals 12.44 degrees. Angle F we found to be 83.78 degrees. And angle T was given as 83.78 degrees. Side S we found to be 12.30 meters. Side F was given as 56.78 meters, and side T was given as 56.78 meters. And so this triangle has one solution. The other solution for angle F turned out to not work by virtue of giving us a measurement of 0 degrees for angle S. We have one last example, and we've seen an example, 2 examples where there were 2 solutions. We've seen an example where there's one solution. We have not yet seen an example where there are no solutions. So we're going to see if that happens here. So the stables need to make a temporary horse pen with some rope. They have 35 feet of rope and plan to tie the rope from one corner of the barn to the tree and then back to the barn in the other corner. So we're making this triangle here. The tree is 21 feet from where the rope is first tied, and the rope and the rope to the tree makes an angle here of 35 degrees with the barn. Okay, so do they have enough rope if they allow 5 feet to tie off the ends? So this is our angle here of 35 degrees. And we know our distance there is 21. Okay, so we know that we have to allow 5 feet of rope for tying, which means that out of the 35 feet of rope, we're going to say that we have 30 feet of usable rope. Okay. So in our triangle, I'm just going to redraw it off of this picture here. This is S, this is Q. We know that distance is 21. Since there are 30 feet of usable rope, if 21 feet have already been used, there are 9 feet left. So we're asking, is it possible that we can complete this triangle with only 9 feet of rope? Given that we can measure this angle here as 35 degrees. So is this possible? We need to either prove or disprove that this is possible by solving this triangle. So I know I've got a pairing of S and little s, and I know I've got side Q here. So the first thing that I'm going to be able to look for is going to be angle Q. So let's set this up with the sine of angle Q over 21 equal to the sine of 35 degrees over 9. With the pairing of S angle S to side S, pairing of sine of angle Q to side Q here. So sine of angle Q would be equal to 21 times the sine of 35 degrees over 9. 21 times the sine of 35 degrees over 9. Sine of Q is going to be equal to 1.34. If I attempt to solve for Q, I'm going to need to do the arc sine of 1.34. And it's going to be undefined, and I can already tell that because I know that the domain of sine, or the domain of arcsine, I should say, the range of sine is what I meant to say the first. The range of sine only outputs values between -1 and 1, and therefore arcsine can only take in values between -1 and 1. So this value is too large, so it's undefined. Right? This is going to be too large. So this triangle has no solution. So this is an example of a triangle with no solution. We've seen them where you know two sides in an angle where there's two solutions. So there's one solution, and now where there are no solutions. So in short, in this example, there's not enough rope. I almost forgot about our last page here, which is on the area of a triangle. You probably recall the generic formula for the area of a triangle. Area is equal to 1/2 times the base times the height. In order to be able to find the area of the triangle using this formula, you do need to know the length of the base of the triangle, and you also need to know the length of the height of the triangle. The height is where it gets complicated because the height is not always one of the sides of the triangle, such as in these two here. It's something separate. It's a measure that I would need to drop down as a perpendicular side in order to find. If we look back at the second page of this section here when we were beginning the topic of law of sines, we talked about those heights right here in being in terms of b times sine of a, or a times sine of b, or so on. And so if I look at my triangle as set up similarly to this one, in this triangle I had ACB, and this one's of course different, ABC. So this side up here needs to be called B. So this looks like this would be, if that's called B, then this is called C. So this would be C sine A in terms of this triangle. If we just relabel this triangle, here when I wrote B sine A, it's this side sine A, which is C. So the H portion right here would be C sine A. So we're able to write the area of this triangle using the same kind of idea we use for law of sines. Let's just look at that how we looked at it originally. If I look at angle A, for angle A, the sine of A is equal to H over C, right? Opposite over hypotenuse. So C sine A is equal to H. So this A stands for area. Got too many A's here now. Area is equal to 1/2 the base times C sine A. And the base of this triangle happens to be called side little b here. So area is 1/2 BC sine A. You're used to using area for A for area, but A is now the name of an angle, so I've got to be a little more careful. That's one of the reasons they're calling area K, is because they can't call it A when A is the name of one of our angles. Too many uses for that same letter. Now we can, of course, drop those hypotenuses down to any side. So the area can be written in a variety of formats. It can be written as 1/2 BC sine A, like we wrote initially. It also could be written as 1/2 AB sine C if you dropped your hypotenuse perpendicular to side A. Or 1/2 AC sine B, similarly if you dropped your hypotenuse perpendicular to a different side. Okay, so these are all formulas for area. They do the same job as the 1/2 base times height. It's just, if you don't know height, you can find it by multiplying the sine A times one of the other sides. In this example, the headquarters of a building is scheduled to be built on an irregularly shaped lot. It is roughly and conveniently triangular. 2 of the 3 sides measure 246 feet and 208 feet, coming together at an angle of 135 degrees. How big is this piece of property in square feet? So it's roughly triangular piece of land. We have 2 sides that measure 246 feet and 280 feet, coming together at an angle of 135 degrees. Now, in order to find area, it's important to note that the angle that you do need is not opposite of the 2 sides that you need. So I don't need side A with angle A. I actually need the other 2 sides. This is exactly what I need. If this is my angle A, this would be side A. If this is my angle B, this could be my side B. And if this is my angle C, this can be my side C. So I happen to have B, C, and A as an angle, so I can use this formula here. Area, K, is equal to 1/2 times 208 times 246 times the sine of 135 degrees. My calculator should still be in degree mode, so I can multiply 1/2 of 208 times 246 times the sine of 135. Comes out as an area of 18,090.6 square feet, which is a good sized piece of property.